Right. Hello. Good morning, everyone from Tokyo. You should be able to see my slides in presentation mode right now. And I would like to start with two thank you messages. The first one, of course, to the organizers and all participants and speakers for this exciting meeting and interesting and inspiring results. And my second thank you goes broadly to all observers out there and for people who provide the data in a format that is understandable for theorists like myself, because the project that I'm about to present is data-driven, and so that would not be possible without all those beautiful data. And so without further ado, I would like to show what we can do with supervised machine learning and how we can infer the multiplicity of the first stars from extremely metal-poor stars. So let me first motivate a problem, not to say conflict, that I see in the stellar archaeology community or how we treat the data. So on the one side, we have stellar archaeologists who, when they observe an exciting, extremely metal-poor star, for example, here, just an idea from Miho Ishigaki. Here, the data points in the background are an observed metal-poor star, and then we try to fit it with supernova yield models. But there we mostly assume one enriching supernova, because that just is easier in most cases. However, if we look into simulations of first star formation, and there was a nice, almost meta study by Hachime Souza. These simulations of first star formation, they show that, so here you see like the time of the simulation and the number of fragments. That is not necessarily POP3 stars, but a good proxy. We see that we have probably dozens of fragments independent of the code and who simulates. And so we find many POP3 stars per mini halo. So we should also expect many POP3 supernovae per mini halo. However, again, stellar archaeologists, for simplicity, assume one enriching supernovae. And so we ask the question, well, can we say if maybe multiple supernovae enrich extremely metal-poor stars? And so a more cartoonish version of this, so this is kind of the standard scenario that people assume. We have the first stars, one star per galaxy, per mini halo. It produces metals, those mixed with the pristine interstellar medium. We form second generation stars, which I would refer to as mono-enriched. However, as I've just shown, we should probably expect from simulation that we have multiple stars and therefore also multiple, probably different supernovae in a mini halo, different meaning, different progenitor mass, different explosion energy, different mixing fallback parameters. And so these produce different chemical abundances. And out of this mixture, we would then form multi-enriched second generation stars. Now, the question is, we can't observe the first stars. We would like to, but we can't at the moment. So my question that I would like to answer is, can we distinguish these two scenarios, so mono-enriched or multi-enriched, by looking at the chemical composition of the second generation stars? Because this is something that we can observe. And so this is a beautiful setup for supervised machine learning. And that's what we did. So we are training support vector machines. I will come to this in 1 second. But the more important question, and I could give a separate talk just about this topic, is how we construct the training data. Because unfortunately, we do not have a ground truth for this problem, because we are the first who try to answer this question. So there is no labeled data set, which means what we do is we go back to synthetic yields of POP3 supernovae. Here we take from Miho Ishigaki 2018. And the mono-enriched stars, we just take the yields basically as they are and we convert it into abundance ratios. And for the multi-enriched stars, we just take random pairs or triplets of synthetic supernova yields. We calculate the abundance ratio. And what you see here is just, you don't have to worry too much about the quantitative details. This is like carbon over nickel and aluminum over manganese. And the distribution, how this would look in abundance space. And you can see that the multi-enriched, the red triangles, are kind of more centrally concentrated in abundance space. And that makes sense because multi-enriched, if you think about it, it's some weighted average of the yields. So this is how our training data looks like. And that's a scatter plot. So there is like a degeneracy in the center. Now, our question is, if we now just have a new observation in this abundance space, can we tell whether it's mono-enriched or multi-enriched? And so what we then get from the support vector machines, I will say a bit more in 1 second, is such decision contours, decision boundaries. And so the support vector machine in this 2-dimensional abundance space would say, hey, when the data point is within this red boundary, it's likely to be multi-enriched, and outside mono-enriched. But you can already see this is highly or quite degenerate. So the answer will not be a 100%, and I will come back to this. But as you can see, in 2 dimensions with one support vector machine, it's degenerate. So what we do is we do the classification in 4 dimensions, and we use 10 different support vector machines. So this is called ensemble learning because we have an ensemble of classifiers that then eventually vote on the final classification. And again, these are just 2-dimensional projections because it's difficult to visualize 4 dimensions. So here it's not so important the quantitative message, but the qualitative idea that we do in abundant space these classifications. And in one sentence, support vector machines, they are a very versatile machine learning method that if the data were linearly separable, then they would try to maximize the decision margin between the groups. In our case, we incentivize it to minimize the distance that misclassifications are away from the boundary. And it's a convex classification problem or convex optimization problem, so it's quite stable and robust. So now, what we do, again, we have, this is like the short machine learning justification slide. So this is the accuracy that we have on the validation training and ensemble validation data. And with the ensemble, we reach roughly 66% accuracy, which is not perfect, but it's the best that the data allows. And the bottom you see, in no specific order, the 10 support vector machines that we use, and the 4 abundance ratios that each support vector machine is based on. This may look arbitrary to you, but also this selection and combination was like the outcome of the optimization process. So this is just to say, well, we tried our best, we reached 66% of accuracy, and now let's look at the results. And at the time, okay, nice. So in our training and test data, just by construction, kind of our prior assumption is that mono-enriched and multi-enriched is equally likely. So we start in the training set with 50%, 50%. In the test set, we nicely recover this trend. So it's almost, the test set is like unbiased, agnostic, it recovers 50%, 50%. But then if we look at the observation, kind of if we take the evidence into account, we see how this shifts, and our otherwise neutral classifier then finds most extremely metal poor stars below metallicity -3 are multi-enriched. And we see that's right 70% to 30%, which seems to be a quite strong indication for multi-enrichment. And on the next few slides, I want to show some more quantitative analysis that we can do. So this is the probability of multi-enrichment. So I said we have some voting of different support vector machines, and so we can calculate the probability of mono-enrichment. And the probability of multi-enrichment is just 1 minus the probability of mono. So just looking at the probability of mono-enrichment is sufficient, which means everything above this line, they are probably mono-enriched. Everything below this line, they are probably multi-enriched. So this is a sample of over 400 extremely metal poor stars. And you can see some trend with metallicity. And this is interesting. And we looked into this more in detail. So you see that at low metallicities, there are more stars seems to be mono-enriched. And thanks. And so here you can see how this looks like in histogram at the top. So if we just plot individually the mono-enriched and the multi-enriched, we see again that at low metallicities, and we're already talking about -5, -6, most stars seem to be mono-enriched. However, at higher metallicities, for me, high metallicities -3, we see stars are mostly multi-enriched, mind the logarithmic axis. And if we bin this and just look at the fraction, then we see that at metallicities below -5, stars seem to be mostly mono-enriched. And if we go to metallicities of around -3, then those start to be dominated by multi-enrichment. And it's just on the side note, it's super interesting and exciting that we see this trend, because on the one side, it is like natural that, well, if you have multiple supernovae, you would expect at higher metallicities. But just what I haven't mentioned before, at no point does our machine learning model knows about absolute metallicities. So we only use abundance ratios, but still we can recover this trend with absolute metallicity, which is really nice and interesting. And so in the last minute on my last results slide, just one additional thing that we can do with this information. So it is a supervised machine learning model, and so we can play with the different input features and dimensions. And what we can calculate is the feature importance. So that basically quantifies if, for example, we would not include iron in the prediction, by how much does the prediction accuracy decrease from our fiducial model. And so here we sort them by the feature importance, and we see that for this discrimination into mono and multi, iron, magnesium, calcium seem to be the most important, the most informative elements. However, this is dominated by the observability. So iron, magnesium, calcium are just easy to detect. And so in the bottom plot, that's like even we don't yet fully understand how to interpret this, but we try to take out this bias of observability. And so we just divide it by the probability that an element is observed. And you can see that now oxygen sticks out, because oxygen has a very small chance of being observed in those extremely metal poor stars. But if it is observed, it seems to provide a lot of information for this classification. And so this is nice and interesting, and hopefully useful for some future observational proposals if people want to motivate why we should observe more oxygen. So coming to my last final summary slide, we have shown that we can use support vector machines to classify extremely metal poor stars, and we find that most of them seem to be multi-enriched. And this is, at least we claim, you can dispute this, this is the first observational confirmation of the multiplicity of the first star. So in our fiducial model, where we need more assumptions, we find roughly 10 POP3 stars per mini halo based on these classifications. Then I showed that this feature importance can be used to, well, first understand what elements are important and what elements will be important for future surveys. And we can extend this on one side to higher metallicities, but also to other chemical enrichment channels, which also means if you are interested to discriminate different subspaces of your chemical space, then please get in touch with me. Thank you very much.
Well, thank you so much, Tilman. That was really fascinating. We have time for a question or two, and we have a couple of questions. So I'm going to go with Simon because I saw his hand first. Go for it.
Hi, Tilman. Nice talk. I'm just wondering if you've tried different supernova yield sets. So I'm not sure how much variation there is between, for example, Alexander Hager's models and Ishigaki's models. And does that affect what sort of fraction you get that's multiply enhanced?
This is an excellent question and a very important question. Thank you very much. So at an earlier stage of this project, we had compared between the Japanese group yields and Higa-Woosley, and it did not strongly affect the results. Okay. And also this specific subset, as I said, I could speak about this for 30 minutes. We can also talk about this offline. Like, we very carefully selected the yields that we use from these catalogs, because we didn't use all yields. Like the yield catalog, there are stars with carbon over iron of 8, which are obviously not realistic. And so we selected what we think realistic subset. And I would imagine if we would apply the same selection of realistic yields to the Higa-Woosley catalog, the results would be comparable. So we haven't tried the Higa-Woosley comparison with the final model, but the tests that we have done so far seem to be robust.
Okay, thank you.